I'm so excited that you have decided to watch this video about the geometric series test and telescoping series test. So let's get started. We have the first example, which you actually could use the nth term test for divergence, which we learned in the last video. And you can say right now, just looking at it, that this series is going to diverge. However, I'm going to teach you another test that might actually be faster in some instances, and especially when the series start to get more complicated. So the first test is geometric series test, which revolves around the central R value. R is like your rate, and really it takes the form, you have like n starting at 0 or 1, or really anything, to infinity, and then you have some r to the n and an a value. In this example, your a value is 1. So what the test says is that if you take the absolute value of r, and if the absolute value of r is between 0 and 1, your series converges. Now, if the absolute value of r is greater than or equal to 1, that means that the series diverges. So in this instance, we can say that the absolute value of r equals 3 halves. 3 halves, that's 1.5, is greater than 1, greater than or equal to 1. So we can say that by the geometric series test, this series diverges. Okay, so let's get on to a slightly more difficult example, nevertheless still very basic. So again, we take the absolute value of our r, which is 4/5, and so we get absolute value of r is equal to 4/5. 4/5 is less than 1, and so the series converges by geometric series test. However, I'm actually going to add in something else that is very important for AP BC Calculus students to know, and that is how to take the sum of a geometric series test. This is why it's helpful to know the geometric series test, because you can apply the sum when you recognize your geometric series. And so sometimes questions ask for what value does it converge to, and of course you can only ask this question if your r value is less than 1. So our sum formula for geometric series is equal to a divided by 1 minus r. And this only applies when your n value starts at 0, your index starts at 0. If the index does not start at 0, say if it started at 1, I would simply replace a with the first term in that series. So if my index was 1, my a value would be 6 times negative 4/5. That's because that would be the first term in your series. So in this case, the first term in my series, when I plug in 0 for n, is going to be 6, because negative 4/5 to the 0 power is 1. And as I said, when the index is 0, your a is always going to be your actual a value, which is 6. So your sum is equal to a value, 6, over 1 minus r, which is negative 4/5. So we can simply reduce that, and I really don't want to reduce much further, but I will. We have 6 over 1 plus 4/5. We can rewrite that as 6 over 5/5 plus 4/5, and we can rewrite that as 9/5, and we can say 6 times 5/9. And I really think that's as far as I want to go, but again, you can pull out a 3, and then we'll have 10 over 3 as our answer. That's the value that this series converges to. Okay, so in our next example, we're going to talk about the telescoping series test. I actually helped you guys out a little bit, because really what this series actually should have probably looked like is that. And it takes a little bit getting used to and which test you can actually use. So I wanted to show you guys this method, or I wanted to show you guys this series in this form, but know that if you'd seen the series that look like this, the same test that I'm about to explain would apply. So I'm going to be talking about the telescoping series test, which is slightly more complicated than the geometric series test, but nevertheless very straightforward. So the telescoping series test relies on partial fractions. So I want to turn this into the sum of two fractions, and that will make it much easier for me to find the convergence or divergence, and you'll see that as I proceed through this example. So partial fractions, I'm going to say 1 over n times n plus 1 is going to be equal to, and then in the denominator, I know that I have these two factors, which are going to add together to give me this number, and I don't know what these numbers on top is, so I'm just going to put variables in for that. So now I can reduce this. I can multiply everything by n squared plus n, which cancels, and multiply this by n squared plus n. So now I get 1 equals a times n plus 1 plus b times n. I'll just put parentheses around that. And now, the cool part about this is that we get to solve for each variable separately, and one of the ways to do this is to choose a value for a strategic value for n. So I can say let n equal 0, and when n equals 0, this whole term cancels, it's just 0. So now I'm left with 1 equals a times 0 plus 1. Implies that 1 equals a times 1 implies that a is equal to 1, and I found what a is equal to. So similarly, I can do the same thing. Let n equal negative 1 to make this term be 0. 1 equals a times negative 1 plus 1 plus b times negative 1. So as I said, this term is 0, and I have 1 equals negative 1 times b. Therefore, b equals negative 1. So now I'm going to rewrite. I think I'm going to run out of time here. I might have to continue this in the next video. I'm going to say that this series, given in the problem, is going to be equal to this, but I'm going to replace my a and b values with what I just found. So my a value, wish I could zoom out slightly, is 1. So I'm going to say 1 over n, series, so n goes from 1 to infinity, of 1 over n plus my b, which is negative 1. I'm just going to do minus 1 over n plus 1. So now the way that I'm going to solve this is actually by extending this out, and I'm not going to extend it out to infinity, obviously, because that would take way more than 2 minutes, or way more than 10 minutes. So I'm just going to show a sample of what this would look like, and this is going to provide us with our answer. So n equals 1, that's our starting point value. So when n equals 1, that first term is going to be 1 over 1, since n is 1, minus 1 over 1 plus 1. Second term is going to be when n is equal to 2. So I'm going to do 1 over 2 minus 1 divided by 2 plus 1. My next term, I'm going to extend off of this index card onto the paper, is going to be 1 over 3 minus 1 divided by 3 plus 1. And this is going to keep going. The nth term of this series is going to be exactly the same as what's up here. And then that's going to keep going all the way to infinity. And I'm going to indicate that with plus dot dot dot. Remember to format it this way, or you will get points taken off on the AP Calculus exam. So now what's significant about this? I'm going to simplify this to make this a little more clear, and hopefully you will recognize that something special is happening